Welcome to all participants to this seminar, Options for Hydrogen in Transport. Bart Somers and I will be your host today of this event. My name is Erik van de Heuvel. I am Director of the Netherlands Platform for Sustainable Biofuels. This seminar is a collaboration between the Netherlands Hydrogen Platform, TNO Automotive, and the Platform Sustainable Biofuels. The webinar is a part of a new fuels and engine program of the platform, and all the focus areas of our platform in this year are developing the context for biorefineries and mobilizing sustainable biomass feedstocks. We have invited Bart Somers, Assistant Professor Future Fuels and Engine Development, and also platform board member, to explore, together with 6 experts, the various options of hydrogen in transport. Before I hand over to Bart, I would like to make some additional remarks on procedures. As you may know, at the end of this session, we have a Q&A session. You have received, if you have registered, a WhatsApp phone number where you can actually bring your message to. Please indicate who you are and to whom you address the questions, so that we can take them in the end of this session and try to answer these questions. For now, I would like to hand over to Bart Somers. Bart, can you shed a little bit of light on why we have this seminar?
Thank you, Eric, for your kind introduction. Well, in Eindhoven, we just started a new initiative, which is called the Zero Emission Lab. That's a collaboration between TNO Automotive, the TUE, Shell, province of North Brabant, and that's basically it. We of course, there is a challenge for future engines. They need to be clean locally and have a low carbon impact. Well, in this seminar, we want to look into what possible low carbon fuels there are available in the future. Obviously, green hydrogen will play an important role in this future economy, but also other low carbon fuels are good candidates. And which viable routes are possible, that will be talked about in this seminar by a few speakers. So maybe it's a good time already to start to go to the first speaker, if I'm correct, and that is Richard Smokers. Richard, you are working as a Principal Advisor Sustainable Transport and Logistics for TNO and representing here the TNO program Voltagem. Voltagem is researching possibilities with e-fuels. Well, my question basically is, what is to be expected the coming years with the production of e-fuels? So please, Richard, the floor is yours, and shed your light and share your vision.
Yeah, thanks for this opportunity, and sorry for a bit of delay. I pressed the wrong button and clicked away the connection. But I'm on screen now. Can I have the first slide, please?
Yes.
Well, the next one then, yeah. Yeah, thanks very much for this opportunity to present the results of a project that has been carried out over the last 1.5 years with a large number of stakeholders. It was a project under the flag of Voltagem and in cooperation with Smartport and a large number of companies and other organizations from the logistics sector, the industry, as well as knowledge institutes, and also wider participation in stakeholder meetings from even a larger amount of companies and organizations. In this project, we made a comparative assessment and some road mapping activities to look at the suitability of e-fuels, including hydrogen and hydrogen carriers, for a number of modalities, including say heavy-duty truck transport, so long-distance trucks, ships, and aviation. We looked at say technical suitability of these fuels, but also at environmental impacts. We looked at various economic aspects to find out which fuels would be suitable for which applications. In looking at the economics, we looked at future costs throughout the value chain to see if, for instance, from a cost perspective, certain fuels might be more interesting than others. And we also checked the requirements that the use of these fuels would have on the renewable energy production in the Netherlands and associated land use. And as a final step, we made an inventory of what kind of actions various stakeholders can take to promote the development and application of these fuels. The results, basically what I'm presenting today is a pitch of the results of this project, so a very small excerpt of what we've done. A paper is in preparation, a vision paper, which will be published beginning of May, hopefully, as a Voltagem vision paper, and this can be obtained by sending a mail at info@voltagem.com. Next slide, please. Yeah. In this slide, you see the different fuels that we have been looking at. It's all looking at e-fuels, so it starts with hydrogen. We looked at a number of hydrogen carriers, including e-LNG, e-methanol, e-diesel, and e-kerosene, and also included ammonia as a non-carbon-based carrier for hydrogen. The graph shows an example of a table, of which we have many more in the reports underlying the paper, from, for instance, the assessment of the technical feasibility of various fuels in relation to the vehicles and the vessels and airplanes in which you use them. So we explored various aspects of technical feasibility, and the table here, as an example, simply shows the assessment of the feasibility of onboard storage for the different fuels in relation to the different applications. And there, of course, you look at energy density, both in terms of volume and in terms of weight, including tank weight and tank volume. Next slide, please. As an example of one of the striking results that we got from the assessment, this slide shows some cost results. We basically assessed the cost throughout the value chain, throughout the energy chain, of these different hydrogen carriers compared to hydrogen for truck transport, for inland shipping, for short sea shipping, and deep sea shipping. And we also have some graphs for aviation, but these are not included here, where you look at production costs, at the cost for compression or liquefaction, for distribution to, say, the filling stations for the vehicles or the vessels, and also to cost associated with adaptations of the vehicle that are needed to be able to use the fuel. And a very interesting result that we got is that if you use, say, middle-of-the-road cost assumptions for electricity and for the cost of obtaining CO2, that actually for most applications, the differences in cost of the fuel, total cost of ownership for these fuels, are very small and are within, say, the uncertainties that are associated with this assessment in any case. We're looking at future costs, so these come with a significant level of uncertainty. So the differences that you see in these four graphs for these four applications are basically within the uncertainty bandwidth that you have for this type of assessment. So basically, with middle-of-the-road cost estimates, the conclusion is that from a cost point of view, there's actually not a single winner for these applications. However, if you go to more extreme cost assumptions, for instance, using higher electricity costs or higher cost for obtaining the CO2, which may also depend on the way in which the CO2 price is calculated, is factored into this equation, then you see that certain winners do emerge, and that in some cases, for instance, hydrogen becomes favorable, or ammonia for other applications. Next slide, please. Yeah. Some more conclusions. These are just teasers to make you interested in the paper. It's by far not a complete overview of what we've done. But if you look overall at, say, the summary of results in terms of feasibility of the different options, there are a couple of clear conclusions. One is totally obvious, and that's from all these fuels. For aviation, actually only e-kerosene is a meaningful and feasible option for replacing conventional kerosene. If you look at e-ammonia, based on the assessment, it's considered unsafe for trucks, but can be used in ships, and is especially from an economic point of view interesting in case of high CO2 costs. The three hydrogen carriers, e-methanol, e-diesel, and e-LNG, are all feasible both for trucks and for ships. And as said, in terms of costs, do not have large differences there. Hydrogen is also applicable for both trucks and ships, but is especially interesting in cases where electricity prices are high or CO2 costs are high, and it's more suitable for shorter distance applications than for long distance applications. We also looked at the space requirements associated with producing these fuels. On my own faces in front of what I'm trying to say. The total demand that we estimated for this type of fuels could be in the range of 1,000 petajoules. The example here is for 960 in the case of methanol. And we looked at, say, the size of these facilities, how much space do the electrolyzers take, the synthesis plants, the capture of CO2. And in principle, this sort of demand, this sort of national demand, could be covered by an area the size of the second Maasvlakte, which is significant but feasible. An important question in that context, by the way, is how much of this fuel you'll actually be needing in the future. And there the graph, the lower right graph is interesting. If you look at the energy consumption for mobility in the Netherlands, there is, say, the domestic consumption used for domestic transport, land-based transport, including passenger cars, trucks, inland shipping, trains, that sort of things. But this is actually only a third, roughly, of the total amount of fuel that is consumed in the Netherlands. The other 2/3 are used for bunkering, bunkering for ships and for airplanes in our main ports, Rotterdam, Amsterdam to some extent, and Schiphol.
Richard,
And an important question.
can I interrupt briefly, because I understood that Bart has a question about the DME.
Okay.
Yes,
yeah.
Yes,
Go
Richard.
ahead.
Very interesting study, I must say. I hope I can get it when it's ready.
Oh, no problem. Yeah.
What I have one question. You specifically put in the mix e-diesel, but you don't mention e-DME or e-OME. Is there a specific reason for that?
Yeah, well, I don't know it by heart. That should be traced back to the start of the project. We started this project, I think, 1.5 years ago. And at that point, in view also of the available budgets, this is not a huge study. There was a lot of stakeholder involvement. The amount of study work itself was rather limited. So that means you have to make certain choices. And DME, OME are very much, say, related to or fairly similar to the methanol pathway. So they're not excluded as an option for technical reasons. They have been excluded just to limit the scope of the work. But at the moment, there are several follow-up steps being programmed for this work. And I think also given the increased attention again for these fuels, they should be included in follow-up steps.
Can I ask also a question, Richard? What do you expect that the timeline of introduction of these fuels will be? For these
yeah, well, that's actually my last graph. So if we go back to the slides, then I'll come back to that question. And so first, just go back one to finish what I was saying here. Important question. Yeah, thank you. Important question for the longer term is whether in 2030 and 2050 we will still be catering for international aviation and international shipping the way we are doing now. Of course, the position of the Dutch main ports, Rotterdam and Schiphol, very much depends on the abundant availability of fuels at low costs. But things may change in view of, say, the transition towards a sustainable global economy. And that has a significant impact on the amount of this type of fuels that you would need within the Netherlands. And also the question whether you want to produce them yourselves or the extent to which you want to depend on import of these fuels. The last graph is coming to your question. We made an indicative roadmap based on say all the stakeholder consultation in the project and the studies that we evaluated. And overall conclusion is that in the next decade you will see increasing amounts of pilots and first pilot plans for production and pilots also on the application side. But I think overall still the consensus is that we will not see significant amounts of these fuels being used before 2030. And I think your question relates to exactly the sort of debate that is now starting on how can we accelerate that in view of the Renewable Energy Directive, the picture that's now sort of clearing up on the demand for biofuel, also from other sectors. The demand for these e-fuels might be larger at shorter timescales than is currently seen in this sort of roadmaps. And I think one of the interesting questions, and that's already popping up also, for instance, in the context of the mission-driven innovation programs that we're now carrying out in the Netherlands, is to see how we could accelerate this sort of developments by looking at what the robust technologies are. And for instance, methanol production could be a robust element of a future system that may, where you at this stage may not yet decide which fuels exactly go to which applications, but where you know that as a feedstock for a number of both industrial and transport applications, methanol could be a feasible first step as a sort of no regret option. Yep. I think that's part of the discussion we need to have in the coming year to really see if there are say clever ways of accelerating this development without making the wrong choices, investing in things that create a lock-in at some point.
Thank you, Richard. Very clear presentation, I must say.
Thanks. You're welcome.
Maybe there will be some questions during the Q&A later on, but for now we have to move over to the next speaker.
Can I just say something briefly before we step up? Because I understood already there are some questions whether the slides will be available and will be shared. Yes, of course, but you can already go to the website www.platformduurzamebiobrandstoffen.nl, and there's on the special team side, fuels and engines, there's a special site on this workshop, and there you will find all the presentations already in PDF format. So that already for those who are looking for the presentations. Okay, please go ahead, Bart.
Thank you, Eric. Richard, once more, thanks for your presentation. So
you're welcome.
It's now time to go over to Stefan Janbroers. Stefan, you are working for TNO as a business developer in the biorefinery area.
Correct.
So obviously, there you are. So you have, I think you have an excellent view on what is possible from that point of view towards the fuels market. So please, if you will, share us your views.
Thank you. I will do so. Yeah, Richard already hinted and mentioned the Renewable Energy Directive. I think it is good to start from that perspective. In the Renewable Energy Directive, it states that in 2030, 3.5% of the fuels should be advanced fuels. And just to give you an idea on how much that is in Europe, to replace the 3.5%, one would need about 100 plants of 200 million liters capacity. And we work in the area of thermochemical conversion, so if people are also in this area, we need 300 to 400 plants of 200 megawatt capacity to just replace the 3.5% of fuels, which I think is an enormous challenge. And I can only imagine that there is not going to be a one-size-fits-all scenario. It was already just shown, I think, in terms of just only liquid fuels, there will be a great demand also in the future for aviation, shipping, and heavy-duty transport. For those areas, it will be very difficult to electrify, for instance, or to find alternatives other than a liquid fuel. For some, hydrogen might be an option. We will come to that in this session, obviously. But there's different transport modes, but there's also different energy sources. And I work in an area a lot where there is a discussion on converting biomass as one of the options, which I think is a great way to at least renew part of the fuels, especially for the liquid fuels that are still required also in the future. So there is different processes, and like I said, there's not going to be one size fits all. I believe there will be different processes, and in these bio processes, and you can think about, for instance, fermentation or digestion, but also gasification. There will be conversion of biomass, so that's basically the long carbon cycle, CO2 taken up by the trees and the agricultural residues, but also in part municipal waste that in processes you can convert to heat and power, obviously chemicals, but also fuels. And when you burn fuels, you will have the recycle of the CO2 again. But during those bioprocesses, also often there is, let's say, a source of CO2 which is very concentrated. And that is a very interesting source to combine with hydrogen when available, because that CO2 from various industrial streams, you can then convert to e-fuels, and then you can look at integration of the biofuels processes with different types of fuels. And that is what you've seen now in this slide, for instance. I've depicted here the gasification unit as we have developed at TNO. It is an indirect gasifier, which means that we exclude basically air, but you get a synthesis gas and some methane typically formed and CO2. And from that product gas, you can make, for instance, methanol. And from methanol, you can go to gasoline and DME. And this is just examples of let's say, the variety of fuels that such a technology can really produce. And it also shows you in yellow the highlighted parts, in this case, where you can have integration options easily with electrolyzers and when you have the hydrogen, but also not to forget the oxygen. Because when you have pure oxygen, you can often also increase, let's say, the efficiencies of a gasifier. If we look at the next slide, it just gives you an example of a process that we are developing within TNO. It's on the next slide, and it's called sorption enhanced DME synthesis. It just shows you that if you have a carbon dioxide source, in this case, to be combined with hydrogen from an electrolyzer, we developed a process where we can, in one step, basically convert the carbon dioxide with the hydrogen towards DME. And in this process, basically 2 steps take place at the same time. One is the adsorption of water, which is formed in this process, and thereby you can shift, let's say, the equilibrium of this reaction to the right side, to the DME side. And that really helps you, because if you don't do this, you end up in first a methanol synthesis where you have a lot of CO2 recycle, and later on a methanol recycle when you do the DME synthesis. So it's an example of an elegant way to do, let's say, electrochemically production of DME. But also this can then be very easily integrated with, for instance, a gasification process, where you have a synthesis gas that is also a combination where you have CO and CO2 and hydrogen, and you can go to a DME synthesis. So those are the things that we are looking into today, and they are downstream of, let's say, gasification options to convert various types of biomass. The question obviously always is this interesting? If we go to the next slide, I try to depict some work from Hanula, who published some work in terms of the pricing, levelized costs of fuel. Because, I mean, for every technology, there is a cost involved. And I don't think we should compare with fossil fuels, because in any case, whatever type of biomass or electrofuel, it will be very difficult to compete, let's say, with the fossil source. But depending on, let's say, especially the price of electricity, when you're talking about electrofuels, it becomes, when the cost of electricity is really low, it becomes interesting to look at these e-fuels, or to have a hybrid version to combine with, for instance, a gasification option. Can also be other types of biomass conversion, but in this paper it is specifically on gasification. And you can easily see in this graph, for instance, the levelized cost of fuel, which is in this case in euro per gigajoule, to just compare these different fuels. I must say that the gasoline in this paper is being produced through methanol, so it is a methanol to gasoline synthesis there. Therefore, the gasoline is always more expensive than the methanol, because it is an additional step. And then you see that the traditional gasification is not. Yeah.
Stefan, can you speed up a little bit because of time?
Yeah. This is almost finished. Yeah. The gasification is a technology that is not so much dependent on the electricity price. The electrofuels is, And what you see is that if the electricity price drops below, let's say, 3 euros per gigajoule, then it becomes favorable to use these fuels, but also the options to combine are in the range of 2 to 6 euros per gigajoule. So think about 1 to 2 cents per kilowatt hour. In the next slide, you see something similar, but then for the biomass, because then obviously the biomass, the price of biomass is very much determining, let's say, the price of the fuel. And just to give you a reference, and you can look it up later, if you look at demolition wood, for instance, that is 1.9 euros per gigajoule. Clean wood pellets are 9 euros per gigajoule. So you're already in the lower left part. So if demand grows, I would suspect that also the prices of those biomass and agricultural residues will increase, and therefore e-fuels become more and more interesting. So in short, we have a challenge. There is a lot to do, and we have to replace a lot of fuels. There is an urgency. If we want to do something in 2030, we should start now. Look at high TRL, like gasification, and as I said, and if things change, we have a larger production of hydrogen, cost will go down. It will be very interesting to combine these technologies together.
Thank you, Stefan. Very clear.
Yeah.
Totally agree with your saying that we should speed up right now. I have one question regarding to your DME setup. You stated it was at TRL 6.
Yes.
What
we are now.
Need?
So the next step, we are building this technology in a container size unit, and we're going to travel around the Netherlands, where we have different sources of, let's say, different sources of CO2, different off-gas streams, and there we are going to produce the DME and do some more testing. But that's the final step before we go to the full-scale production, I would say.
So you take the CO2 from industrial processes.
Exactly.
As a sort of carbon capture.
Yeah. So there's different technologies that can be enhanced, but it can also be just an off-gas where you have some CO2 in it. Because this sorption enhanced technology that works really well, so you can easily do these two steps in one. So it doesn't need to be directly pure. It does help.
Okay.
Yeah.
That's it. Okay. So sorry, we're running out of time, Stefan. So this is the only question I can pose right now. Otherwise, I would have had more. But
perhaps there are some
thanks
later.
very much. Maybe later in the Q&A. Sure. So we hope to keep you online.
I will be here.
So we move on to the next speaker, and that actually is Xander Seikens. Xander, you work at TNO Automotive most of the time, but part-time you're a colleague of mine. I know you did a study on the possibilities to use hydrogen directly in a combustion engine, and I think most of us are very interested in the results of that study. So please, if you want, share this study with us.
Hi.
Yes, welcome everybody. Bart, thank you for the introduction. Indeed, the study is a DKTI study, a feasibility study on hydrogen combustion, funded by RVO, MPS Diesel, and TNO. If we go to the first slide, actually, yes. So first question is, why internal combustion engines? There are mainly 4 important reasons for this. Firstly, the internal combustion engine is a robust and proven technology, not only in road but also in non-road applications. It's of course an established industry. We know how to design and optimize engines, manufacture them, service and maintenance them, and we also know how to recycle them. It's tolerant on hydrogen fuel quality. So purity requirements for hydrogen are less strict as, for example, for fuel cell application. Also in combination with natural gas and hydrogen, hydrogen fuel quality plays a less dominant role. And last but not least, the internal combustion engine, as I will also show later, has the potential to run without after treatment, and then you don't need any precious metals or rare metals, which also reduces the environmental impact of the system. So all in all, the internal combustion engine on hydrogen in this case enables accelerating the energy transition towards a sustainable society, and it provides an interim solution for many applications for as long as they cannot be, for example, electrified when that is not available or even possible. So on the next slide, I've shown here a graph to illustrate why the combination of hydrogen and the internal combustion engine is very interesting. Main reason here is that it does has the potential to provide high efficiency in combination with very low emissions. The graph shows the NOx emissions and the efficiency as a function of the air excess ratio, lambda. We all know that from thermodynamics, efficiency gradually increases with the air excess ratio, which is shown by the green line. And NOx emissions are typically highest at slightly lean conditions and then gradually reduce when the mixture gets more lean. That's shown by the red line. One very nice property of hydrogen is that you can burn it in a very lean way. If you take it in comparison to, for example, natural gas, then natural gas has a limit of about lambda around 2, where hydrogen can be burned steadily and stably well above 3. And if you look at this graph and we look at the dotted purple line at the bottom, at the very bottom, which is the NOx limit of current legislation, the Euro 6 stage 5 legislation, then we see that for air excess ratios above around 2.2, that NOx emissions are already below the legislative limit, which also means that above this limit you don't need any NOx after treatment. And that is one thing that we can exploit with the hydrogen engine when we run it in a lean burn fashion. So that's one of the concepts. Another concept is of course the stoichiometric engine, where we do have a lot of NOx, but there we have the proven technology of the 3-way catalyst to reduce all the NOx to acceptable levels. And in intermediate lambda ranges, we also have the dual fuel solution where we combine hydrogen and diesel, where we can make use of diesel-like after treatment, the SCR technology to mitigate the NOx. So these are already several concepts that we can use for the hydrogen engine. On the next slide, I've made a comparison between these concepts, a high-level comparison between these concepts relative to diesel. So here the diesel engine is shown with 100% power density and efficiency of around 46%. So if we look at the concept of the stoichiometric engine, the lambda 1 engine with after treatment, engine after treatment system, then we see that this engine has a relatively low efficiency, very typical to normal gas engines, around 37-38%, where mainly the throttling losses reduce the efficiency. And power density is lower as a result of the displacement of air by hydrogen through the injection of the hydrogen in the intake. And also specifically for the lambda 1 engine, the NOx tendency is very high, which also reduces the maximum allowable load. As said, a very interesting concept is the lean burn spark ignition engine, with the potential of also running without after treatment. It's also a 100% hydrogen solution like the stoichiometric engine. And here you can benefit from the faster burn of hydrogen to have high efficiencies, diesel-like and potentially even higher than diesel. And again, a slight reduction in power density is seen here, which can be partly mitigated by applying EGR, and also in the future maybe by applying direct injection of hydrogen technology. And finally, we also have the dual fuel solution, combining diesel and hydrogen, where the CO2 reduction is of course much less than 100%. Here 30 to 60% is feasible. Efficiencies in range of diesel and a slight reduction in power density. As a fourth feasible concept, there is a future concept which is the combination of hydrogen and argon. So here we replace the air by argon, which has a much higher specific heat ratio, which enables much higher efficiencies, potentially even in excess of 60%. It's a future concept, which is also currently in development, for example, at the Eindhoven University of Technology. So what are then the applications of the hydrogen engine? That is shown on the next slide. So for these different applications or different concepts, there are also different applications targeted within different time frames. So here, if we look at the 2020-2025 time frame, we mostly see the hydrogen, or foresee the hydrogen engine for off-road application, where the dual fuel application is feasible for shipping, near coast, inland shipping, and also tractors. Not 100% hydrogen solution. For the 100% hydrogen solutions, the main target applications in this time frame are the stationary power generation, where the stoichiometric hydrogen engine with three-way catalyst may target the lower power ranges, and the lean burn concept without after treatment targets the higher power range. If we look at the 2025-2030 time frame, there we see a more transient solution feasible, where we combine the hydrogen engine as a range extender with a battery in a hybrid truck or a tractor. And as a further outlook beyond 2030, we have this high efficient argon hydrogen engine for stationary power generation, high power generation with local hydrogen generation as input to this power plant. So there are quite a variety of applications possible where we can benefit from the fact that it is a zero emission, close to zero emission technology, based on proven technology with a high efficiency and with a slight loss in power density, which, as already mentioned, could be mitigated by future technologies like direct injection hydrogen technology. So as mentioned, I think the hydrogen combustion engine enables an acceleration of the energy transition for many applications, for as long as the alternative powertrain solutions are not available or even possible. And with that, I would like to conclude.
Thank you, Xander. We already got a question through the Q&A, which I want to pose you right away. It deals with the, you claim that the power density of a lean burn hydrogen engine is low, but are there no ways to overcome that power density issue by turbocharging extra?
Of course, by the application of EGR, you can reduce lambda a bit, again, without increasing the NOx emissions, which already reduces the loss in power density. And at the same time, the EGR is used to extend the NOx limit, which also allows you to generate more power from the engine. so that are already next to future technology like direct injection hydrogen, that are already means to reduce the loss, potentially to no loss at all, but that is also part of research.
Okay. Thank you. Regarding time, again, this is the only question we can pose right now. Maybe later during the Q&A. Thanks again. And now it's time to go to the next speaker, which is Peter van der Heijden. Peter, you are the Managing Director of NPS Diesel. And your company is an expert on diesel applications and also on modifying diesel engines. And I think you have an interesting story to tell here on how you did that with hydrogen. So please, if you will, be my guest and share this with us.
Good afternoon. Thank you for inviting me. Thanks to the speakers in front of me, especially Sander, for his clarification. Very interesting. I'm left over with the easy part, not technology, but the market side, which is of course interesting when you want to innovate a new product and bring it to the customer. We are introduced as a diesel expert, which is true, but over the last few years, we tend to move to more sustainable power solutions, which we do like and which our customers like. And maybe we can go to the first slide to clarify that a little bit. Can anybody hear me? Okay, thank you. The reasons for considering hydrogen in an internal combustion engine are, for us, very clear. We have many customers knocking at our door, like, can we switch from diesel to a new power source? I think yes, we can. And some of our customers are looking at hybrid electrifying their machinery. But they have the machinery in a remote area, so the electrical grid is not able to provide them on short term with the power they need for charging their machinery. A possible solution could be that you have local power plants running on hydrogen with an internal combustion engine that provides the power for charging systems for that machinery. That's one specific application we are looking at. The other one is very obvious, on-site power demand, like festivals, like construction areas. Everybody knows the recent problems why we all drive 100 kilometers per hour. There's a lot of focus on clean power solutions on every construction site where there's a diesel generator. The near future could be that those generators could be replaced by internal combustion engine that run on hydrogen. That's the same more or less like a growing demand on mobile power systems that are on festivals, that have a moving place that can be running on hydrogen. And the other thing is the market we are in is a very conservative market. They are a bit afraid of sometimes electrification, fuel cell technology because of their cost. It's very sensitive. They like the current diesel engines, to say. If we could provide them with a similar product that is very resistant to vibration and, like Sander says, fuel quality, environmental impact, they would like to have that product. So there is a market demand, which is good, I think, on short term for such an engine. Next slide, please. It's not a secret. We are investigating at the moment the Dutch-built DAF Packer 11-liter platform. We would like to start this year. We are already doing some research work in front of this project. The aim is to start field endurance testing in 2022. The nice thing is that we have already partners in the project that actually are demanding such an engine. They feel like if you can bring it tomorrow, we're open to support you, which is nice. And like Sander expressed in more detail, I think the modern diesel engine is very much suitable to use as a platform for hydrogen because of the ability to resist high peak fire pressures. It is equipped with high pressure cooled EGR. So it's not a copy-paste product for hydrogen, but the platform is very much suitable as a starting point for developing an engine that can cope with the current diesel engine when it comes to power density in the future. Next slide, please. Some applications. Yeah, this is, like I said, a typical application. Bredenoord is one of the partners in the project that has a very high interest in these type of solutions. As I mentioned, the electrical grid is not always ready to cope with the high peak power demand due to electrification, due to solar power. It's getting more dynamic, which means that we could help the electrical grid by installing grid solutions that run on clean fuel, and a conventional generator run on diesel could be replaced by a generator set running on hydrogen to make it clean. I have another example. This is another partner in the project. It's a firma Herema. They have sustainability very high in their strategy. They are currently building big wind farms near coast on the North Sea. During this construction, they are not allowed to exceed a certain noise level, and to prevent that noise level, they have a curtain of bubbles in the seawater to protect animal life in the sea from a high noise level. It's also measured, it's restricted, it's by law that they have to do this. And the funny thing is they make a green wind farm, but in order to have that curtain of bubbles, there's about 20 diesel-powered generators on board of the vessel. You can see it laying close to the platform on the picture, producing all the air, the pressurized air to create those bubbles. And they have a special request, and they would like by tomorrow or next week to have those diesel generators replaced by generators that run on hydrogen. And they have many of those vessels. You can imagine how many emission they are producing at the moment, and they would like to have them clean in the future. Then I have, I think, a conclusion on my last slide. Again, in our world, our customers are still looking or requesting very robust power solutions. Again, they are used to the diesel engine. If we could replace the diesel engine by a hydrogen engine, they would be very happy. It's very well accepted. I think there's a very low cost of ownership compared to alternative clean solutions. When you look at the hydrogen engine, the maintenance cost, the lifetime, the no after treatment solution, if you calculate that all down, the capex or cost of ownership can be very well acceptable or close to the current diesel engines, and even maybe a little bit lower. There's no precious metal used. It's a non-complex technology, not meaning that it's ready tomorrow, but the components we need to use to develop this engine are available. So we think there's a fast time to market. Again, if we could start the project this year, the end of 2022, we would be able to start field testing. And if that all goes well, I think well before 2025, there could be a market introduction of these type of engines. And then the last point is important, of course. We need an infrastructure. like I was told in the beginning, the price of the fuel, the availability, the infrastructure to get the fuel on remote areas where the customer wants to use the engine is, of course, a need. Otherwise, it's a nice project that will not work. So it all needs to come together at one point in time. That's finally what I would like to say. Thank you for
Thank you, Peter. Thank you, Peter. There is a question already through the Q&A, and that's a question I also had. So for this development of this hydrogen engine, you need special components, obviously. Do you already have suppliers for that?
Good question. We have options for that. We have suppliers, but we have options for that. Yeah, but it's not fixed now because we're just starting the project. So we are looking for components to fit on the engine, but it's in process.
What is that you think the biggest problem you will encounter?
I think Sander is also aware of that, but I think the matching of the turbocharger, because of the low energy content in the exhaust, could be a hurdle that we need to take, and that could be a cost-consuming, time-consuming part of the project.
Yeah,
I think. Yeah.
So you're going for a lean burn variant then?
Yep, we will go for a lean burn variant, aiming without after treatment. Aiming at about 80% of the original torque curve of the diesel engine. So that's more the goal we want to reach. Yeah.
Okay. Thank you for this presentation, Peter. And I'd like to be kept informed on this. It's very much on my.
Thank you for your time. See you.
Okay. Well, it's time to move to our fifth speaker, and that's Max Aerts. He is the founding father of this company Dents, who is developing applications using formic acid. And Max, please tell me, how did you come up with this idea on formic acid, and what is you think the big gain on this compared to other applications of hydrogen?
Yeah,
so just do your presentation and we'll see.
Thank you for having me. Can you hear me?
Yes, we can.
And
the
slides are coming up.
Appearing.
Yes.
Okay. Yeah, so how we came up with it's actually a big coincidence because it was actually discovered on Eindhoven University of Technology, a catalyst that was able to convert formic acid into hydrogen really rapidly, and that's how it all started. But at the end of my presentation, I will also highlight the roadmap a bit that we've been following over the last few years. So yeah, regarding the slide that is displayed at this moment, it's a bit the way it works, but I guess for all the participants, it's quite obvious. From carbon dioxide, water, and electricity, you can make multiple fuels, amongst which also formic acid is an option. It's a very simple molecule that's actually a hydrogen molecule glued to a carbon dioxide molecule. And what we do as Dents, we have developed a reformer that is able to convert the formic acid back into hydrogen and carbon dioxide really rapidly at pressures between 0 and 1200 bar of pressure. And we can do, of course, multiple things with that. So in this image, it's shown that the hydrogen and carbon dioxide combination gas goes into an ordinary PEM fuel cell, and there we generate electricity, and then the emissions are carbon dioxide and water vapor. And yeah, the same emissions are used as the building blocks of the fuel, and therefore it's completely sustainable. Next slide, please. Can you go to the next slide?
Yeah, we are. There is a bit of delay. It will be no soon.
Okay. Let me see. Great. So what I tried to display over here is when you look at the top. Sorry. One of the upsides of using formic acid as a liquid fuel is the fact that it's a liquid at atmospheric pressures and temperatures, and that you can handle it in a relative safe and same manner as you are doing with diesel at the moment. So depending on the fuel quality, the flame point is below or above 60 degrees Celsius, which has a huge impact on the safety regulations, of course. So regarding the infrastructure, the liquid infrastructure can actually be reused, depending of the material type of the infrastructure, of course, but it's low tech and comparable to what we already have. In the upper case, on the right top side, you can see equipment. You see a power generator and an excavator. What we do there is we integrate a reformer into such a piece of equipment, and the hydrogen and carbon dioxide gas that's being produced can either be used in a combustion engine or in a PEM fuel cell. And that's when we integrate the reformer into equipment. But what we also can do is place the reformer somewhere in the infrastructure, for instance, on a hydrogen refueling station, and there you can produce clean hydrogen on demand from the liquid storage up to pressures 1200 bar, and of course 900 is the pressure that you need there. And we've then done a feasibility study together with Pitpoint, and the conclusions there were that we have potentially cost reduction of 50% in capex and 10 to 20% in opex when you compare this hydrogen refueling station to a hydrogen refueling station that is relying on compressed hydrogen gas that has to be shipped there. Next slide, please. So, in short, the main advantages of hydrogen. Hydrogen is actually the brand name of the fuel that consists largely of formic acid with some minor additions. The energy density is quite high, 1.8 kilowatt hours per liter. Of course, when you compare it to diesel, it's nonsense, but it's relatively good, and you have 53 grams of hydrogen per liter, and that's also quite nice. As mentioned, it's liquid, limited safety risk. It is, of course, an acid, so that's something that you have to take into account, but it's not explosive or flammable. Currently, we are 100% focusing on the construction sector. So on the right bottom side, you can see our first power generator that's actually used on a construction site to charge electrical equipment. And the upside, of course, is it's no noise, no emissions, electricity on demand, and since the fuel is a liquid, it's quite convenient to use and highly comparable to a conventional diesel power generator. Next slide, please. So this is actually the timeline that I was referring to in the beginning of my presentation. So in 2015, we started this development at the university, and after a few months of experimenting in the lab, we have created a small car that could drive on formic acid. Then we founded the student team and built a 1 meter scale model of a Porsche. After that, we came into contact with VDL, who asked if we could make it for a bus. We've took on that challenge, but it was just a bridge too far to scale it up 1,000 times and then also make it mobile applicable. So that's why we have chosen to put it in a stationary pilot project together with the BAM in the construction of a road in The Hague. and that was in June 2018. After that, we've founded Dens, and we have made a few prototypes, and currently are working on the 25 kilowatt prototype, and that should be finished in this summer. And from next year onwards, we actually want to start to produce these generators in series production. Yeah, that's it. So currently it's TRL 7, and before the end of the year, we would like to reach TRL 8, and then hit the market, so to say. So that's the story from our side.
Thank you, Max. We got a question, and it refers a little bit to your excursion towards VDL, actually, where you try to make this mobile application. And the question here is can you make this work for a small system like in a truck?
Oh yeah, definitely. We have no doubts about that. The only thing why we didn't fully succeed in making it drive with the VDL bus is that we were not far enough yet with the technology. So we didn't have enough experience, and the system that we eventually made was too big, and it was not suitable enough to really drive on the road. But if we would do it over again, yeah, definitely.
But then it would be sort of a backup charging station in a truck, right? Because your maximum power is like 25 kilowatts, as I see it.
Yeah, the 25 kilowatt now, that's the choice that we've chosen now, but we can also do 100 or higher. That's just depending on the fuel cell that we choose. So there's no real restriction in scaling that up.
Any plans in going that direction?
Yeah, so for the stationary market, we will start the end of next year a development of a dedicated 100 kilowatt system. But in beginning of next year, we will already cluster 4 25 kilowatt systems into 100 kilowatt system. And space is not really a restriction on the construction site, so we can do that easily in a larger sized container.
Thank you. Very interesting.
Thanks, Max.
Keep us posted on the progress.
Yeah.
And then it's already time for the last speaker of today. And that is Mr. Ilko Dekker, who is a big methanol lover, let's say. He's a chief representative of the European International Methanol Institute. And of course, he will focus on the use of methanol. So please, Ilko, share your thoughts with us.
Thanks very much, Bart. And I realized that as the last speaker, I'm already 7 minutes into the time that was originally scheduled for questioning. So I'll be brief. If we can go to the first slide, please. So as a quick word on the Methanol Institute. The Methanol Institute is the global industry association for the world's largest methanol producers, distributors, and technology providers. And it won't come as a surprise to the audience that we are very glad to be able to participate in a workshop which is primarily focused on hydrogen and not so much methanol. So I was quite pleasing to hear the first two speakers mention methanol very frequently. And it actually makes a lot of sense because methanol as a molecule actually contains to a large amount hydrogen. As you can see, there are 4 hydrogen atoms and only 1 carbon and 1 oxygen atom in a methanol molecule. And when we talk about alternative fuels, I often mention one of the big benefits of methanol being that 1,000 liters of methanol actually contains more hydrogen than 1,000 liters of hydrogen does. And I won't go into the specifics of why that is, but roughly speaking, you can calculate back that a cube of methanol contains approximately 3.3 times more energy than a cube of hydrogen at 700 bars does. So when the objective is to find a pragmatic way of distributing hydrogen in the existing transport market, then methanol is a very convenient way of getting the hydrogen molecules to the end user. If we can go to the next slide, please. One of the key purposes when we talk about hydrogen or alternative fuels in that sense in transportation is the fact that we're trying to reduce the carbon emissions from transportation. And that also means that where conventional methanol today is being produced from natural gas primarily, we need to find alternative pathways to produce methanol from biogenic or renewable sources. And as was mentioned by Mr. Jan Bruce from TNO, there is no such thing as one simple solution. There is no silver bullet. And the same can be said for the different production pathways for renewable methanol. If we look at the ways that renewable methanol is being produced today, there are quite a few different pathways. Probably the best known example in the Netherlands is BioMCN in the Delfzijl, which is using biomethane as an alternative to conventional methane to produce biomethanol. And biomethane is made through the fermentation of biomass. But that same biomass can also be gasified to produce a syngas from which methanol can be made. A good example is the Enekem project in the port of Rotterdam, which aims to convert municipal solid waste and other waste streams into methanol. But only last month, for example, Södra in Sweden announced that they've started to produce methanol from their pulp process, which is a kraft process. In that process, they are able to distill the methanol from one of the waste streams. So those are some examples of biogenic pathways to produce biomethanol. But obviously in the context, especially when we talk about hydrogen from renewable resources, a lot of attention goes to the alternative way of making methanol, which is to use renewable electricity to produce hydrogen through electrolysis and then react the hydrogen with carbon dioxide to form methanol. Probably the best known example of a company that does exactly that is carbon recycling in Iceland. But closer to home, there's a big project in Sweden called Liquid Wind, which aims to produce e-methanol from offshore wind power. And even closer to home in Germany, Total intends to produce e-methanol from the carbon dioxide from their own refinery. And as was mentioned in the first presentation from Voltechem, methanol cannot be used in jets, although it can be used in turbines, but that's a different story. But you wouldn't want to use methanol as an aviation fuel. But there's a project in the port of Hamburg where they intend to convert methanol into kerosene. And that is why methanol makes a very interesting hydrogen carrier, because irrespective of which fuel ultimately has preference in the market, methanol is a very versatile product that can be converted into a range of different fuels for conventional diesel engines, spark ignition engines, and fuel cells. And that's the next part of my slide. So if we can go to the next slide, please. For those of you who are familiar with the use of methanol as a fuel, we often hear reference to the fact that methanol is being used primarily in China at 15% in gasoline engines. But as you can see from this picture, which is quite busy, these are examples from all over the world of various methanol fuel applications. And in the interest of time, I'm not going to go through all the individual examples. Instead of that, I made the next slide, which helps to structure all those different examples. And I'll spend a bit more time focusing on these different examples. And again, here you can see the three different categories of engine technology coming back. We have the combustion engines, which are split into spark ignition and compression ignition, and then we have the fuel cell technology. where methanol is being used primarily as a hydrogen carrier. Now, in spark ignition today, where China focuses primarily on 15% methanol use in standard road vehicles, in Europe, we're testing, amongst others in Italy with Fiat Chrysler, but also with BMW in Munich, a blend of 15% methanol and 5% ethanol. And the reason for doing so is because with existing conventional unmodified engines, it helps to reduce the tailpipe CO2 emissions, which is a practical way for these OEMs to get closer to the 90 grams per kilometer threshold that they're required to meet. But in a spark ignition setup, you can actually go to 100% methanol. And the bubble that you see in the cars column is a picture of a fleet of more than 10,000 Geely taxis that operate on 100% methanol in China. And Geely actually has a factory in China where they can produce over 100,000 M100 vehicles per annum. But they don't only have an M100 technology spark ignited for passenger cars. They actually started selling a truck that runs on 100% methanol in spark ignition mode. And last year, they showcased this technology in a rally car that participated in the Dakar Rally. And it actually did finish. I think it was in the top 15, if I'm not mistaken. Now, because methanol has a very high octane, typically, most certainly those in the car industry associate methanol with spark ignition engines. But for us in Europe, the use of methanol or alcohol fuels as an alternative to diesel is very interesting as well. Probably the best known example is the use of methanol as a fuel in dual fuel engines, where you have a fuel oil or a diesel fuel as a pilot fuel, but the bulk of the energy actually comes from the methanol. And one example is the use of methanol as a fuel in dual fuel engines for international shipping. MAN from Denmark is supplying large two-stroke engines for international shipping. There are currently 11 chemical tankers that operate on methanol, and there are, as to the best of my knowledge, currently 7 more vessels on order. But that's not the only way you can introduce methanol in combustion ignition engines. I think most of you, especially Bart and others from TNO, you are, I'm sure, familiar with the ED95 engine that Scania supplies for trucks and buses. But the interesting thing is that that same ED95 engine also operates on methanol. So if you change over the ethanol for methanol, the engine works just as well. And that, yes?
Sorry to interrupt, but can I ask a question? What do you think is necessary and how quick needs, let's say, the capacity buildup for methanol production, renewable or bio-based, or how do you see that time frame for the coming years?
It's always a little bit a chicken and the egg question, obviously. You know me quite well, and my personal opinion is that fast is still not quick enough. So we definitely need to ramp up that scale. But you can imagine from an investor's perspective, you will only start committing funds to those types of projects if you know that there will be demand. And the demand will only be there if there is sufficient capacity. But it is comparatively easy to scale up those capacities, in part, and the best example I think is BioMCN in the Netherlands, where they have succeeded in taking an existing asset and switch over from a fossil feedstock for the production of methanol to a renewable feedstock. Now, that's a relatively easy thing to do. So that means that with the given capacity to produce methanol in large-scale units, it's relatively easy to increase the amount of renewable methanol that can be produced in existing assets. When it comes to projects like the example in Sweden, liquid wind, that requires several years, but it's still can be done within a relatively short time frame, provided that the legislative foundation to make that happen and to make that feasible is also available. I hope that answers your question, Eric.
I hope so too. Eric, did it answer your question?
Yes, of course.
Of course, he says. There's already one question from the Q&A, but I thought you already explained that. But the question is really why methanol is not picked up in ship diesels. But I think it is.
It is, and maybe if we can go back to the slide that maybe helps the viewers see the different technologies, because I can imagine that for them it's not easy to recall all the different examples that I've listed here. So absolutely, methanol today is already being used in large ship engines, and as Methanol Institute, we are working with various consortium partners to introduce methanol for short sea shipping and inland waterways as well. We actually have a cooperation with the TNO and the Delft University, which focuses on precisely those markets, inland waterways and coastal shipping. It's called the Green Maritime Methanol Project, where we are trying to introduce methanol as a solution for those types of markets. There's an international consortium with Lund University, which has received Horizon 2020 funding for the so-called fast water project that looks at developing high-speed engines. But besides methanol as an energy carrier, and it was mentioned a few times in previous presentations, and you had a question about that as well, Bart, methanol is a very interesting product to convert into other energy carriers as well. I didn't include the example of methanol to gasoline, but I did include DME and OME. DME, dimethyl ether, is basically for diesel engines what LPG is for gasoline engines. So it's the gaseous products, but the very interesting benefit of DME is that it can be used in standard diesel engines with very minor modifications. You need some changes in the seals and everything, the ECU, but it still operates on full diesel mode. OME is actually it's oxymethyl ether, which is a liquid form, but also derived from methanol. It can be blended into diesel. Typically, that is something that is still very much in an early TRL level, whereas the DME technology has already been demonstrated by Volvo in Sweden probably over a decade ago. Today there are Volvo and Mack trucks operating in the city of New York, demonstrating the use of bio-DME from a factory out of California. So one of the big benefits of those ethers is that they avoid the typical trade-off that we see between NOx and soot emissions. So normally either you decrease in soot and go up in NOx, or you decrease in NOx and go up in particulates. And by using either DME or OME, you can reduce both aspects. And maybe if we can just show the slide briefly again for the viewers.
I was about to, let's say, close off, Eelco, just because of time considerations.
I appreciate that.
Into the Q&A.
But if you allow me one brief minute, the only point I wanted to make is because the aspects I mentioned just now were all combustion engines, but the title of the workshop obviously is hydrogen. There are fuel cell technologies that use methanol as an energy carrier, either for direct methanol fuel cells or in the form of reformers, where you then split the methanol between hydrogen and carbon dioxide, and then the hydrogen is used in fuel cells. And to just close off with the question about shipping, there's a project which is called the HyMeth ship, where we are reforming methanol on board, capturing the carbon on board, bringing it back to shore to convert it back into methanol, and actually combust the hydrogen in a ship engine for main propulsion.
Utterly interesting,
Okay.
Eelco.
Thanks.
Thanks for your presentation.
My pleasure.
Bart, we have now, let's say, have seen your 6 experts sharing their various views on the topic. What do you think, and that can kind of kick off the Q&A session now, what do you think, what are for you the main takeaway messages from these presentations?
Well, what I've learned is that hydrogen as such could be a very viable fuel for combustion engines, but there are also many, and they are actually equally expensive or viable derivatives of it. So I think what we need for a clean future is to develop these pathways quickly. And that is something that really should be high on the agenda, is make sure that we develop these crucial pathways towards fuels that are clean and can be used in combustion engines.
Mm-hmm.
And secondly, I think we have to make very good choices. For instance, methanol, we know methanol is a system chemical, so we really need it for all kinds of applications. But it's also a perfect gasoline. So if we could restrict in some how do you say that, fancy way or smart way, the number of fuels we choose, but are usable in current engines, but might have synergetic even gains in future engines, then we should go ahead as fast as we can and go and set up these production pathways. But make smart choices.
Mm-hmm.
Not try to make everything. Make only a few, but good ones.
Yeah. Well, thank you. Yeah. What I saw as a kind of an eye opener in this is that the way, let's say, hydrogen goes into the system actually has different ways, and there seems to be a lot of synergy where you can actually link the hydrogen to another carrier of that hydrogen and the energy of that hydrogen, so that you can actually, let's say, benefit from existing infrastructures or from easiness from being it, let's say, for temporary at least in the part of the chain,
Exactly.
being a liquid fuel.
Exactly.
Yeah.
Totally agree.
If I am correct, there are some questions now, and I understand there were some questions directed to Xander. So we have invited Xander back on screen again. Well, hi there again, Xander. I'll have to take the questions from there. Yeah.
Yeah.
So how to compare the dual fuel hydrogen and diesel system in comparison with the synthetic renewable diesels, like for instance HVO? Have you heard the question, Xander?
Yeah, I've heard the question, and I interpreted the question as a question about the difference between well-to-wheel and tank-to-wheel.
Not necessarily, I think. But if you can shine a light on that, shine your light on that already, that would be helpful.
So with the HVO, of course, well-to-wheel, you are okay. It's CO2 neutral. Tailpipe, still there is some CO2 which you have to put currently against the legislative limit, where the hydrogen part, of course, also reduces significantly tailpipe CO2, also in the dual fuel application, where of course the diesel part can also be an HVO fuel.
If I may add on that, Xander, on a tank-to-wheel basis, HVO, or so let's say renewable fuels, are viewed also as a zero emission because of the short cycle that the carbon loop is, and because it's also closed cycle. So that is indeed, there is 3 issues: well-to-wheel, tank-to-wheel, and your tailpipe emission.
Yes, correct. So
there is another question here, I think.
Yeah.
Oh yes, the question to you is indeed, if we pose the question to you, whether you then could repeat the question for the participants.
Okay.
He has received 2 questions. Okay. So, well, this is, let's say, through our channel, live stream channel. I think one of our colleagues have sent you directly questions, I think via WhatsApp or via email.
Yeah.
So if you could have a look at those and then repeat these questions and give them to us. So this is a kind of a 4th dimension to this live stream, so to say.
Yes. So basically there were 2 questions, both related to power density. One question states, please explain the power density of lean burn engine. For the lean burn engine, it is pretty high for high efficiency and limits from the turbo, but perhaps you know how these can be overcome. And the second one is also related to reducing the loss of power density, where it is stated that reducing lambda will increase NOx, and the use of direct injection may also increase NOx due to shorter mixing times and ridge zones. So firstly, the loss of power density. The main reason for the loss is the replacement of the air by hydrogen, such that you cannot put all the hydrogen in together with the air that you want at a certain lambda, which makes that the power that you can achieve is reduced, also because there are limits to your turbo, to your air part. Ways to mitigate that is by, for example, replacing some of the air by EGR. If you do that, it is correctly stated, lambda reduces again, which might result in more NOx, but the recirculated excess gas, as we all know, is a good measure to reduce the NOx again, which in the end may limit the penalty on NOx. Furthermore, the use of EGR with water, with also a bit of NOx in it, is a good way to extend the NOx limit a bit, so that you can achieve higher power output, which of course then increases power density. Direct injection, on the other hand, then you are not replacing any air at all. So you can run a lambda 2.5 and then put in the desired amount of hydrogen directly into the combustion chamber, so not into the manifold, not replacing any air, which allows you to have an increased power density. And that effect is dominant over a loss that you might have by reduced mixing times, which could result in stratified mixtures, maybe even some ridge zones where NOx emission might still occur. So there, the increase in power density is by the elimination of the replacement of air by hydrogen is a dominant factor.
Thank you, Sander. Thank you for this explanation to these questions. I understand we have a room for one more question, and this question goes to Max. So thank you, Xander, once again. We're now going to reconnect with Max for a last question, and then we're about to close off this seminar. Hi, Max.
Max is frozen.
We're just waiting for the connection with Max for the time being. Yeah. Hi, Max.
Yes.
Hi. Okay. There is a question here, and that says, why embrace hydrogen? Because diesel and DME have a higher energy density. Could you detail about that?
Yeah, I think why embrace hydrogen when
hydrogen, your formic acid product.
Yeah, I understand.
Okay.
But hydrogen is actually a hydrogen carrier, and it's best to use for a fuel cell. And DME and diesel, obviously cannot be used for that. So I stated in my presentation that it is possible to use the combination gas that's produced from hydrogen in a combustion engine. But I think it's indeed favorable to use diesel or DME in a combustion engine. So I think that is the answer.
Okay.
to that.
Yeah.
So use it in a fuel cell and not in a combustion engine. Then I think that explains a lot of everything.
Well, thank you for that clarification, Max.
Yes.
Thank you. Then I'm about to close off now this webinar. We have seen a very wide range of presentations of how hydrogen might, let's say, be used in the transport sector. The slides are available via our website. Also, the live stream will at some point in time be available for those who missed it now. But I would like to thank all of you participants for your presence in it. Even though we can't see you in real life, we very much appreciate that you have been here and listening. And from the questions that we saw coming in, we have seen that you have been active and reactive. So thank you very much for that. Furthermore, I would like to thank, of course, Bart for his hosting of the event and for asking some interesting questions also to the presenters. Of course, I have to thank our presenters as well. So Richard, Stefan, Xander, Peter, Max, and Ilko. Many thanks to you for sharing your views on this. Then some last words. I think a special thanks should go to Peter van Gompel of TNO. He actually ignited this workshop when he started to think of, together with Loes, of, well, how could we bring this topic under consideration. I would also like to thank Loes Knotter, also from the Platform Sustainable Biofuels, also in setting up and designing this workshop, both from content side as in the way we present it to you. I would like to thank Leon van Wezenbeek because of his excellent technical support to make it happen as well. And again, all participants, thank you. Stay connected, stay safe in this time, and look forward to seeing you in a next webinar or any other next event related to sustaining and making transport more climate neutral. Thank you very much.